Welcome back, physics fans. Today, we're going to go back to Newton's second law of motion and find out what happens when we use the kinematics definition of accelerations. We know that Newton's second law is deceptively simple. F equals m times a. Well, there's more to it. For one thing, the kinematics equations will factor into this because we are dealing with motion, and the definition of accelerations. We can use the definition of acceleration and Newton's second law with mass, initial velocity, final velocity, and acceleration time. We can use that to determine the force needed to change the motion of an object. Accelerations, remember from kinematics, a is v minus v naught over t. Parentheses are important, or final velocity minus initial velocity divided by time. Combine that with Newton's second law, and with a little algebra, I can solve these problems in only one step. F equals m, the quantity v minus v naught over t. And you might be tempted to do this, and there are problems where this is certainly appropriate. There will be other problems where we'll solve them step at a time. What's the acceleration? And then, what was the required force? So, Newton's second law and acceleration. Well, you know me, brand new shiny physics equation. Let's take her out for a test spin and see what happens. Whenever I have a problem, first thing I have to do is a physics student on a snowboard with a combined mass of 90 kilograms starts downhill. You know, snowboarding. Gotta be a cool cat somewhere up in the Rockies fixing to bomb a hill. Well, if that 95 kilogram student starts down the hill with an initial velocity of 2.5 meters per second and then accelerates to 18 meters per second in 7.5 seconds, determine the student's acceleration and the force pulling the student down the hill. I've read it. So after I read it, and there we go, bombing the hill. 95 kilograms, we start at 2.5 meters per second and accelerate to 18 meters per second in 7.5 seconds. Read it, diagrammed it. After I diagram it, I list the mass of 95 kilograms, the initial velocity at 2.5 meters per second, the final velocity at 18 meters per second, the time of 7.5 seconds, what's the acceleration, and the force. Well, I need to solve for acceleration. So the acceleration equation is a equals v minus v naught over t. Don't have to do any algebra, and parentheses are important. Plug and chug, go. What is the acceleration of our student? Indeed, 2.07 meters per second squared. But what was the force pulling that student down the hill? Well, for that, the deceptively simple Newton's second law, F equals ma. Or the mass and the acceleration, go. Right, 186.62 newtons. That's how much pull is taking you down the hill. Newtons, the unit for force, is named for the cookie, the Fig Newton. No, it isn't. It's named for Sir Isaac Newton. And actually, in the English system, we use pounds. But let's look at our second. A red Dodge truck with a mass of 950 kilograms accelerates from rest to a final velocity of 55 meters per second in 2 seconds. Wait. 55 meters per second, that's 130 miles an hour. From 0 to 130 in 2 seconds? There isn't any truck does that. Well, this one did. That's Bill Maverick's Little Red Wagon, a popular attraction on the NHRA circuit. While it is quick, its whole goal isn't to go as fast as it can from one end to the other. See, Bill Maverick, and then later his sons, were capable of driving the front wheels with the steering wheel in the front, turning these as the traditional mode goes. But they were also attached to the boogie wheels in the back, so that he was able to use those to control the direction the car is going in as well. And then Bill Maverick would stand on it, and up it came. For the entire quarter of a mile, this dragster would pick the front end up and go from one end to the other, dragging sparks all the way. Quite the fan favorite. But wait, what kind of a truck is that it can pick the front end up in the air? Well, it does help that he was using a 7.7 liter, 500 cubic inch, multiport fuel injected nitromethanol burning Hemi Chrysler engine into a special transmission, and up she goes. So our little red Dodge truck with a mass of 950 kilograms accelerates from rest to a final velocity of 55 meters per second in 2 seconds. Determine the acceleration, truck, and the force applied. I've read it. After I read it, the next thing I do is, and here comes our little red wagon rolling down the track from 0 to 55 in 2 seconds. Now I list the mass at 950 kilograms, the initial velocity 0 meters per second, the final velocity 55 meters per second, and the time of 2 seconds. What is the acceleration and the applied force? Well, the acceleration equation, A equals, correct. And remember, parentheses are important. Plug and chug, go. What's the acceleration? Indeed, 27.5 meters per second squared. So what force was that drivetrain capable of applying to the little red wagon? Newton's second law, F equals ma. With a little algebra, I get 26.125 kilonewtons, 26,125 newtons. Yeah, that'll pick the front end up in the air. Not only that, it's 3 G's. That'll slam you back into your seat. So Newton's second law, F is ma, A is V minus V naught over T, and I can combine them when I need to. F is m, the quantity V minus V naught over T. When next we get together, we'll see what happens with Newton's second law, a little algebra, and the big 6 equations of kinematics.